lower bound do you know? Sorting lower bound, that is probably the only at least one lower bound bit we do not know, right. So, you want to sort n numbers, the comparison based lower bound tells you that you need at least n log n comparisons, omega n log n comparisons. How do you prove that? Right. What is the tree? Comparison tree. So, you model any sorting algorithm, comparison based sorting algorithm, what would it do? It will make a comparison. You know, your input is x1, x2, xn. So, right. And this is decision tree. So, for sorting you have x1, x2, xn which you want to sort, and the only thing you can do to know anything about these numbers is to make comparisons, right. You can't look at an xi and say is it 23, is it 47, no, you are talking about algorithms that learn anything about it by making comparison between pairs of elements, and based on the outcome of the comparison it does some of the thing, it makes more comparisons, that is all it does. For that kind of algorithms we want to prove lower bound. So, this is first thing about lower bounds is that you have to be very clear about what is the model, what are you, I mean we are talking about some restricted set of algorithms that do sorting by doing these kind of things. So always lower bounds come with some caveat, something about what model. So, here in the comparison model, any sorting algorithm, if all it is allowed to do is to make comparison, it will pick some xi and xj, and you have this less than, equal to, greater than. Let us assume that all elements are distinct. So, there are no equal to, because again, so what does that mean? Then I am talking about not only restricted set of algorithms, restricted set of input, okay. But if I show lower bound on a restricted set of input, that is still good, right, that is strong. Even on these input, it is going to take more time, kind of thing. So, maybe this branch does not even happen. Now, so what will the algorithm do? It will pick some other comparison. In this case, it will do something else, and depending on some outcome, it is going to branch like this, right. So, take a typical any sorting algorithm that will sort 5 elements. What will it do? It will pick some pair of elements, compare, based on the outcome you will make another comparison, and so on and so forth. And when do you stop? When you have the sorted order, which means that you have figured out somehow that x1 is less than x7, is less than x2, is less than x4, is less than x5, is less than something like this, which you have figured out in one leaf, then you know that you have sorted, right. But if your outcome took you to some other branch, maybe you will end up with some other leaf and you will have some other permutation of the input, right. So, any comparison based sorting algorithm can be modeled like this when it is trying to sort distinct numbers, because that is all you asked. You allowed the algorithm to do only make comparison. What else can it do? It only choice it has is which pair of elements to compare. So, this is how any algorithm, any comparison based algorithm. So, pick any comparison based algorithm, you can model it like this. The only thing that will be different between different algorithms is what indices you are comparing in each of these nodes. Okay. So, what are some observations about this algorithm, which is modeled as a binary tree? The number of leaves would be how many leaves will there be? n factorial, right? Isn't it obvious? I mean, is that clear? Have you seen sorting lower bound, Ryan? You have, right? Okay. So, number of leaves will be n factorial because, I mean, let's write a sorting algorithm for 3 elements, right? x1, x2, x3. You know, without loss of generality, I am going to compare less than, greater than, maybe x1 and x3. Suppose less than, what do you get? We know that x1 is less than x2 and x3, so x1 is the smallest, but you still don't know anything between x2 and x3, so you'll make another comparison. And now if it's less than, then you know that x1 is less than x2, less than x3. In this case, x1 is less than x3, less than x2. And in this case, what do you know? You know that x1 is greater than x3, but less than x2. So we are done, right? Are we? I claim it is this, because this tells you x3 is x1 is greater than x3, and this tells you that x1 is less than x2 because this is the U path. So you have sorted it here, actually, right? Now, in this case, you may do something else, and you realize that every leaf should have some permutation. Why? What if it's not the case? Suppose you have a sorting algorithm which doesn't have any, and how do you rigorously argue that it is not correct? That is what we will eventually, in many of these lower bounds, we will say that if the algorithm didn't do this, it can't be correct on all the input. So, suppose let us say I have this sorting algorithm modeled as this comparison tree. In some leaf, I mean, you look at all the leaves, maybe some permutation pi is missing. So what? Then it cannot. So if I give you, so suppose 1, 2, 3 is missing, then if I give that kind of an input, then it won't be able to sort. The algorithm is not correct on all the inputs, in particular in this kind of thing. It might go and get into some other leaf and it will be wrong. Okay. The number of leaves must be n factorial, and worst case number of comparisons by this algorithm, what does it correspond to in the tree? Right. So, for example, this algorithm stops with 2 comparisons sometimes, 1, 2, 2 comparisons, you got the answer. Sometimes they needed 3. So, what is the worst case number of comparisons which corresponds to measure in the tree? It's the height of the tree, right. And this is true for any comparison based sorting algorithm. We have not fixed for any, take any comparison, merge sort, heap sort, whatever, model it like this, because that is all it will do. I mean, of course, apart from making comparisons, it will do some moves, it will do some pointer changes and so on, fine. We are only counting number of comparisons. Then that should have this many leaves, and height of the tree is what I care about, which is the worst case time. Now you can, it is a binary tree. If you have a binary tree with some k leaves, then the height must be at least log k. Okay, this is another separate lemma. Since this sorting algorithms of n factorial leaves, the height, so the worst case time must be at least log n factorial, and log n factorial by Stirling approximation is omega n log n. It is close to, right. So, hence or and this is close to n by E log n. Now so this is one lower bound, but is it tight lower bound? Maybe there is something better lower bound. Asymptotically, no, because we know we can sort in O n log n. But if you read, here is an interesting open problem. We don't know a sorting algorithm that can sort using at most log n factorial comparisons. Not theta n log n, not omega n. I want log n factorial plus maybe some smaller order term. Okay. We don't know, it's still an open problem. So, in fact, Knut started out a project to figure this out, and he did up to n small numbers, and maybe he found some 40, some number. So, it has been, what is the optimum number of comparisons to sort has been figured out, I think, for small values of n, maybe up to 50, 100, I don't know. But in general, is there a sorting algorithm that performs at most ceiling log n factorial comparisons plus some smaller order term? We don't know. Okay. But asymptotically, it's theta omega n log n, and we have heap sort, merge sort, they all perform theta n log n comparisons. Okay. So, this is one way of proving lower bounds. This is essentially, this is also sometimes called information theory lower bound. You can think of it as I am trying to get, what is the information I am trying to figure out in this sorting algorithm? I am trying to figure out what is the permutation of the given input, right. Ultimately, when you finish the sort, you know what is the permutation of the sorted order of the given input. And there are n factorial possible choices, and in one comparison, you are sort of trying to reduce a certain number of choices. And it's a binary tree, so you only, if you make one comparison, you know that if xi is less than xj, then all permutations where xi is greater than xj is ruled out. That's only half the permutations. And so you need, you have to gather a certain amount of information. Each comparison gives you only this bit of information. So you need a lot of information. You need a lot of work to get your information. So this is sort of the argument. So it's typically log of the number of possibilities is the kind of argument. Okay. Most often it doesn't really give you very tight lower bound. But let me just give you some exercises to try. Merging, right? If you want to merge a list of size m with a list of size n, okay, you have a sorted list of size m. So, lower bound using this decision tree method, which is basically everything boils down to figuring out how many leaves are there, right, in this comparison model. So, optimum number of comparisons, But if I want to, let's say, apply this to find the maximum of a list of n numbers or something, what are the possible leaves? How will you model? So, and again, let's look at a comparison based algorithm to find the maximum, right. So, you make a comparison depending on the answer, you make, if it's less than, you do this, if it's greater than, you do this kind of comparisons. And what are the leaves? N leaves, right? The leaves are only the indices of the maximum. So, there are only n possible choices. So, if you apply this, you will get a lower bound of like log n, right. Lower bound is lower bound. 0 is always a lower bound, right? 1 is always a lower bound, you can say. So, it's a lower bound. But it's not, we know we can prove something better, right. So, sometimes it gives you I mean, it at least helps you number of possibilities, may not always give you correct or good lower bounds. So, we want to I'm going to spend time talking about adversary based lower bounds. Okay. Okay, so this is not decision tree. Okay, so you can think of an adversary which is giving a worst case input. Okay, so let's understand the question. What does it mean by a problem can be solved in some f of n time? Let's say a problem pi okay, let's write this in some logical formula. Okay, so pi could be sorting and fn could be n log n, okay, asymptotically. So sorting, you can sort n order n log n, right. So in general I can do matrix multiplication in n cubed order n cubed time. What does it mean? Can you just tell me logically? I want with there exists for all kind of quantifiers. What does it mean by pi can be solved in f of n time? For all okay, for all instances of pi, what does can be solved mean? What does that mean by can be solved? Can you say that again with some logical quantifiers? There exists a, what is solution here? There exists an algorithm, right? There exists an algorithm A that answers whatever question or solves pi. Okay, now you know an understanding of what does it mean by A solves pi, right? A is some algorithm which will sort, which will matrix multiply in f of n time, or you can say for all instances of pi of length n, it's not completely correct, and that's why Ryan is laughing. What's the problem here? So let's read what it says. For every instance, you give me an instance, I'll give you an algorithm. You give me another instance, I'll give you another algorithm. That's why we have written here. So how do I fix it? Oh, if you give me x1, x2, x1 to sort, if it's in this order, I will apply merge sort. If it is in that order, I will apply heap sort. That's the way we have written. So what's switch the for all, right? There exists an algorithm. There exists one algorithm for every input. Right? There exists some algorithm. Let's say merge sort. There exists merge sort for every input of size n. It will actually sort in order n log n time. There is one algorithm. You can change the algorithm, it will maybe f of n will change. There may be many algorithms, but that's okay. All I am saying is there is some algorithm which will actually for every input it will solve, right? Right? Now, can you say this logically? because that is what we want to show, right. We want to show lower bound. We want to say that algorithm cannot be, the problem cannot be solved in this much time. That is exactly the statement about lower bound. How do you negate this statement? What is the negation of this? I mean, that does not exist, yeah. So, I mean, there does not exist an algorithm that will solve all inputs in f of n time. Okay. What does that mean? Yeah. So, there is no algorithm, that is what it means, that for every input of size n, it will answer in f of n time. Okay. Can you say it as for every algorithm A to solve pi? Now, can you complete it? There exists an input on which pi will take more than f n time. Right. So, I am going to actually say cannot be solved in less than or equal to f of n time. That is what I want to show. Right. So, this is what. Okay. Now, we will do this using adversary. What does that mean? That it is a two-player game. Okay. You say I am the algorithm, I am the best algorithm, right, for every algorithm. So, I do not know what your algorithm is. You come back and say I have this algorithm. I am the adversary. I will look at your algorithm and say here there is here look at this input. On this input your algorithm will take more time, and this is how we will argue that we will argue this, that cannot be said, right. So, I am adversary. So, the adversary's job is to produce this bad instance for every algorithm. The problem is I do not know your algorithm. So, and important thing, look at the quantifiers, there is no universally bad input. For this algorithm, here is this bad input, but on this input your algorithm may do better. Okay. But for your algorithm I will provide you, because this there exists comes after for all. So, this input depends on the algorithm, right. You give me an algorithm, I will give you this input. For that algorithm, I will give you this input. For that algorithm, I will give you this input. It will take more time. And so, this is what is adversary strategy, right. But the problem is I mean sometimes, okay. So, we will do a lot of, I mean it looks complicated on the face of it, but we will look at examples. Okay. So, often the adversary's job, so sometimes the adversary may not even look at the whole algorithm and then give you the input. It may even it will generate the input on the way. Okay. So, right. So, let us look at the max finding problem. So, given a list of n numbers, I want to find max by making comparisons. The claim is cannot be done in less than or equal to n minus 2 comparisons. I want to show that any algorithm to find the max. So, it is like this. Okay. So, that means I have to look at every algorithm in the world and provide a bad input which will take more than n minus 2 comparisons, right. So, how am I going to do that? Well, it is a comparison based algorithm. So, I will let the algorithm ask questions and I will answer, right. I am adversary. So, what are you going to say? Okay, x5, x7 which is smaller, right. So, I will answer. I do not. So, important thing is I do not even have to, as an adversary, I do not even have to have the whole input in front of me first, because the input depends on the algorithm, right. So, as you keep asking, I will sort of generate my input in my mind and I will give you at the end, here is the input. for which your algorithm will take long time. Okay. So, for max finding, the adversary is actually very simple. What is adversary? I will actually have some list. Okay. So, maybe x1, x2, xn. Okay. This is not usually, I mean, adversary is a lot more powerful, but as an adversary, what I will do, I will pick some n numbers and answer accordingly for every comparison. Okay. So, you are going to ask me questions, I will answer accordingly, right. But remember, I never tell you what x5 is, what x7 is and so on. All I tell you is x5 is smaller than x3, bigger than x6 depending on the kind of questions you are asking. And I have a choice of how I want to make x5 at the end, whatever I want, as long as consistent with the answers I have given, right. So, what do? I just, in this case, as I said, adversary is just dumb, it does not do anything, it just fixes an input and keeps answering. Okay. Now, suppose you finished your algorithm and you performed n minus 2 comparisons. So, here is an algorithm that asked these questions, I answered it with my input I had in mind and I answered n minus 2 comparisons. Okay. Then now we went through this before. So, what happens? Yes, do the connected components. So, what do? I have this x1, x2 up to xn. I will draw the following graph. For any comparison you ask, I will draw an edge. Suppose you ask x1 and x7, I had my input in mind, so I will answer which is smaller, which is bigger, and I will draw an edge, okay, undirected edge. Since you only asked me n minus 2 comparisons, this graph is not connected, right. So, I have this at least 2 connected components. Okay. So, on these vertices. Now, you are going to tell me some vertex here as the answer, right. You say, because you finished, you said I am done, I made only n minus 2 comparisons, I found the maximum, you will say x7 is the maximum, right. Now, what can I do? I will say no. Why? Because I will pick some number which is the largest in this component and I will say this is the maximum. And I never revealed you what the numbers are. I have a choice now, I can do it. Now, the important thing is I should have choice to make x12 number maximum consistent with all the answers I have given, right. But remember, since this is disconnected, you did not ask me any comparison between an element here and element here. So, if I have made x12 much larger than x7, of course, it has to be the largest among here, right, because I cannot make the smaller number and make that the largest, because I am bound by whatever I have given. So, among these elements, whatever the largest, I will make it larger and say no, you are wrong, because x12 is larger than x7. So, this is the adversary strategy here, it just sleeps, fixes an input, answers accordingly, at the end it wakes up and says, you are saying this is the maximum, no, the input I had in mind, because I have my choice, I never revealed you what the input is, this is x12 is much larger than x7, here I mean I will instantiate my xi's with some numbers and I will tell you this is what I had. Of course, it has to be consistent with all the answers I gave, and that is correct, because you never asked me anything between these two, because that is why it is disconnected, right. So, that is, so for now remember, this is the input I am giving you is with respect to the algorithm, because if you asked a different algorithm, I will have a different set of connected components, I would have instantiated into different set of numbers, okay. And the key thing is that you need at least n minus 1 edges for a graph to be connected, and that is what we are using it here. Okay, here is another searching a sorted list if you want, or guess my number, right. I think of a number between 1 and n and you are going to ask me yes or no questions and guess the number, and you know what is optimal strategy for you, right? Or rather, what is one strategy for you? If I think of a number between 1 and n and you have to ask me yes or no question and get the answer, what strategy would you use? Binary search, right? You just go to the middle, compare and so on. How can we show that that is actually optimal? That you can't do better than this? So, this is the usual question I ask. So, what number should I think of so that I will be forced to ask you a lot of questions, right? I am thinking of a number between 1 and 1024, let us say, and you are asking me questions based on yes or no questions. I am an adversary, right, because I am trying to show lower bound. I want to say that any algorithm, I do not know what questions you are going to ask, any algorithm must perform at least log n many questions is what I want to say, right. So, what number should I think of? To make you work hard? You see that this is exactly what we want to prove, right? We want to show lower bound, right? So, what should be basically in trying to show this lower bound, you have to have an adversary strategy. How should adversary answer, right? Because comparisons are coming. Best algorithm is making comparisons, and my job is to generate an input. The only thing leeway I have is that it's comparison based thing, so I don't have to reveal you the number. I just have to answer the comparison and finally instantiate them, right? So, what should be the adversary strategy? One and 1024. The usual answer is maybe you should think of close to 1 or close to 1024. You are laughing. Why is it not correct? Don't think of a number is the answer, right? Because look, I have a choice. Why do I want to? Whatever number I think of, you might ask that as a first question for all you know, because I am playing against any algorithm, right? So, I do not know what question you are going to ask. So, why would I think? Even in the max finding, right? Okay. So, this is the difference. In the max finding, I actually said I will have an input and then answer accordingly until the last minute, and then I will just wake up and say, okay, this is what I had and so on. In this case, I will not think of a number because it is dangerous to think of a number, right. So, I would just wait, because remember, this is where it is interesting. I can't put a there exists before. There is no universal input which is good for every algorithm. There may not be. Sometimes there may be, I do not know, but may not be. So, why would I want to? I will wait for your algorithm and then think of an input, right. This input depends on the algorithm. Okay, now what should be the strategy? You still need a very specific strategy so that you can prove a log n lower bound. Do not think of a number is correct, but then he is going to ask, is it greater than 57? What should I answer? Exactly. The strategy, the adversary strategy is, see, remember, I had n choices initially, because it's anything between 1 and n. Once you ask a question, I will say, okay, if I say yes, how many choices will be left? If I say no, how many choices will be left? Pick answer in a way that the number of choices is as large as possible, the remaining choices. So, if it is 1 and 1024, and if you ask is it less than 57, I will say no, because less than 57 there are only 56 choices, but greater than 57 I have lot of choices. So the adversary strategy, so if you have to prove a lower bound rigorously, you actually need to come up with an adversary strategy, then argue that with this strategy any algorithm must perform at least so much comparisons or whatever, right. So the adversary strategy is, because it's a Boolean thing. If I say yes, it lets you with some choices. If I say no, it lets you with choices. These are disjoint choices. Okay. And so I will measure and see how many, which is a larger band I have, and I will answer it in that way, so that. So now what can you guarantee? At least after every comparison, at least half is left, right? Because so that this is where the algorithm meets the lower bound. So the best algorithmic strategy is to go and ask the middle. The best lower bound strategy is to make sure that at least half is left. So because you don't ask the middle, I will actually make you work harder by giving you the larger choice. So now you have actually a recurrence relation for the lower bound now, right? The lower bound would be T of n is greater than or equal to, in one comparison, adversary ensured that at least n over 2 is left. So this shows that at least log n. So because and do you realize that finally I am actually thinking of a number and giving you a number, right? Because if you ask is it greater than 57, I am supposed to think of a number between 1 and 1024, and I will say no, yes it is greater than 57, and I will mark it in my notes. Okay, the number I am thinking of should be in the range 57 to 1024. And then you ask another question, oh, is it less than 85? I will say no. Then I know that I am thinking of this number here. Okay. Finally, if I had a lot of choices and you stopped and said, yes, I found your number, you are obviously wrong, because I have, it's like this kind of a game, right. If you said this, I will say, no, this is what I thought, and it will be consistent with whatever I have answered. So the only time where you can stop is when you have narrowed down to one number as my range. So both of us are playing the same game, which is, what is the game of reducing the number of choices, the range. We start with 1 to n and we are reducing the number of ranges. You are playing the same game, you want to get there fast, I want to make you get there slowly, right. So the adversary strategy, you need to spell out the strategy. Strategy is answer comparisons in a way, a larger number of choices are left. Okay. So here adversary cannot wait till the end, it has to be very active adversary, it's answering, unlike the max finding algorithm, the max finding adversary. Okay, let's do max and min. And often the challenge is to actually figure out what is it the algorithm is trying to do, what is it, then capture it in some parameters, then we can play around with it. Okay, so that's a useful thing. Or basically what is the algorithm state at any point of time, right. In that binary search thing, the algorithms or the adversary state is that what is the range now you have narrowed down to, that is the state of the algorithm. Okay. Once you capture that, then you know that that's what you're trying to, algorithm is trying to minimize, adversary is trying to maximize it. So in the case of min and max, we need to figure out what is the adversary algorithm state at any point of time, right. It's just making comparisons. Okay, first of all, let's look at an algorithm. What is the best algorithm here, or whatever best or something we will prove, lower bound. But how many comparisons can you find the min and max? We saw that some time back, but it's also probably there in the first problem sheet. Hmm? 3 by 2n, yeah, it's more precisely remember how does the algorithm work? Find the largest using this tournament method, right? Pair them up, the winners move to the next round. So, that is n by 2 plus n by 4 plus n by 8 plus n by 16 all the way, and you will get the max, and this is n minus 1 comparisons. And then exactly. So, you take the first round losers, n over 2 of them, and find a min among them, and that is only n by 2 minus 1. So, it is n by 2 n minus 1 plus n by 2 minus 1. Is clear? You see the algorithm, right? Just max finding algorithm, but we do not do the single pass thing, but we will do tournaments. So, you have this, but that also takes n minus 1 comparisons. The advantage is now first round losers are the only candidate for the min, and there are only n over 2 of them, you just find the min among them. Okay. Now, I want to show that this is optimum. I mean, you can't do better, right, using adversary argument. Okay. So, adversary is so often you can also think about, if I want to prove some algorithm is optimum, or I mean this adversary argument kind of work close to the algorithm, because if you look at it, this adversary argument tells you what should be the best algorithm strategy is, that go always ask in the middle, because otherwise you are going to lose out, right. So, that is a binary search. So, similarly, you can always turn an algorithm into an adversary into an algorithm, and so that is what you are going to. So, essentially you are going to show that this algorithm is an optimum algorithm, you can't do better than that. So, for that let us capture the state of the algorithm. Okay. So, at any point of time the algorithm has made some comparison. So, what is it trying to find out, right? If you want to say the max finding algorithm, what is its job? Its job is to involve elements in comparison, so that everybody except one has at least lost one comparison, right. That is because until if two people have not lost any comparison, then you are not done. That is what this we used it in the adversary, right. So, everybody must have lost at least one comparison, then everybody except one has lost at least one comparison, then that is max finding algorithm's job, right. Make comparisons, so that, because as soon as somebody is lost you can eliminate it, and that is how it is doing it. In this case, if in that language, what is the job of the algorithm which finds min and max? So, let me set some state here, right. So, let us say L is lost all comparisons involved in. Suppose this is a set of elements which have always lost whatever comparisons they have been involved in, and similarly W is won all comparisons involved in. Let us say LW is lost some, won some, and N is never been involved in a comparison. So, let us partition my players into these sets. Okay, this is a partition, because take any player, either never been involved in comparison, or among the comparisons it is won all, lost all, or some lost some. Okay. And let us look at the cardinalities of these sets. When you start, what can you say about what is this 4 tuple? before any comparison has been made. This is n 0 0 0, and when you end, what do you want? The end is the important thing, right? What do you want at the end? Zero, 1, n minus 2, 1. That you want exactly one element which has lost everything it's been involved in, exactly one which has won everything which has been involved in, and n minus 2 must be here, right? Because with any other configuration, you have not solved the problem. In any other so in this case, you know that this guy is the min, this guy is the max. In any other case, you can't concretely say that this one element is a min or one element is a max, because you will have choices. So now you can think of it as the algorithm is moving from this state to this state, both algorithm and the adversary are. Algorithm's job is to get from here to here very fast, and adversary's job is to make you move slowly. Okay. So once you sort of captured the state of the algorithm, the adversary strategy is fairly straightforward. Okay. You can figure out what the adversary should do, because it's like this binary search. If I answer this way, the algorithm is gaining a lot more information than if I answer this way, so I will answer it this way. That's how the algorithm will do. So that's what we will do here also. So, but let's see what that strategy should be, right? Okay. So what is that algorithm's job? Make comparison. What is adversary's job? Answer the comparison, right? So the algorithm comes and asks, okay, here is some x, here is some y, tell me which is smaller, right? This is what the algorithm is asking. The adversary, depending on where x is from, where y is from, it's going to answer it. Okay. What are the possibilities? Suppose x is in and y have never been played. You can answer arbitrarily, right? It's an easy case. Let's say the state of the algorithm is, let's put it in small numbers, n, I don't want to say n because n is the total number of elements to start with. So let's say some k, l, w, this is the number of, at this point, before the algorithm made this comparison x, y, the tuple, this tuple, let's say it's this value. Okay. Now, at the end, the algorithm answers this arbitrarily. So what happens to this tuple? K minus 2, yes, L plus 1, LW, W plus 1, because you made one guy win, one guy lose. So number of winners increases by 1, number of losers increases by 1. This doesn't change. Number of people who have never played drops by 2. Okay. So you can write such things. So if both of them have lost whatever they have played so far, again you can answer arbitrarily, and you can appropriately change the values, right? So what will this be? If both of them have always lost so far, then L would go down because one of them will increase to this. This is the new state, right? Number of people who have never played hasn't changed because these guys have played before. I'm forced to make one of them win. There are no ties. Okay, forced to make one of them win. So one of them actually moves to the LW bucket because they have lost some and won some. So that one actually, it moved from here to here. and the W remains the same, whoever has won continued to win. So, this is a new state, right. Similarly, if both are W W, then again it will be K L, LW plus 1 will increase, W will go down, one of them will move here. Okay. So, these are cases where the adversary does not have to work hard, it just answers arbitrarily. But let us look at a case. Suppose X is lost all the games so far, Y has won all the games so far. How would you answer? I will again answer in one way, see the new state, answer in another way, see the new state, and whichever is to my advantage, me meaning adversary, I will answer it appropriately. So, how should I answer? So, okay, suppose I flip, suppose I say the guy who has lost so far is going to win now and this guy is going to lose. What happens to this tuple? LW will increase by 2, this will decrease by 1, this will decrease by 1 in one case, right. This does not change. But if I say no, the guy who has lost continues to lose, the guy who has won will continue to win, what happens to the state? Nothing changes. So, that is what I will give. Yeah. Remember what is our goal? We should remember our goal. I want this coordinate to go very fast to n minus 2. Why would I want to give you 2 here? This is 2 information, I will not give you that. So, I will say whoever has lost continues to lose, whoever has lost. So, that means you stay in the same state, right. So, the adversary. So, here adversary has to wake up, you can't just answer arbitrarily, it will say, because otherwise the algorithm is gaining lot more information. Okay. So, here I will say X loses, Y wins and the state remains the same. So, this is what I meant, once you capture the state of the algorithm, what the adversary should do is fairly straightforward, because you just have to say, okay, how does the state change, which one gives me better advantage, I will answer it appropriately. Okay, so you can go on. So, how many more left? There is a lot of things left, right. So, LW and W, LW and L, these are all the choices. Same thing, right. If a LW player plays with W, if I make him lose, then LW coordinate increases. I do not want to give that, because I can continue to say that this guy wins, so that the state does not change. Similarly, here I will say this guy loses, the state does not change. What other case left? LW, I can answer arbitrarily. So, what is, if you say you have to write rigorously what is the adversary strategy, this is what adversary strategy is, that for every type of comparison I should know how to answer, that is adversary strategy, right. So, the comparisons there are more, there is N and L, what should I say? So, somebody was never, because I do not know how the comparisons will come, somebody was never played and somebody was lost all the time, what should I say? The loser loses, because if I say the loser wins, then LW coordinate is going to increase, and this will move to L or W, I do not have any choice anyway, that is not a problem, but I do not want the LW coordinate to increase unnecessarily, because that is what the algorithm is trying to get. So, the choices are natural, right. So, NW, so there are all possible NLW, every possible thing based on what the state happens, and you have a strategy. Okay. But now we have to, where is this number? How do I show this, right? So, you can think of it as I have this huge state diagram, a graph, where every node is like a tuple, right. Every node is a tuple, and you draw an edge, a directed edge from this tuple to that tuple if some comparison leads you from here to there, right. And what are you now looking for in this graph? Shortest path, right, because the algorithm shortest path from here to here. So, right. So, algorithm state is a tuple of these numbers, and you draw an edge from one tuple to another if one of the algorithms comparison will take you from here this state to that state. And we know this is the edges, right. If you are in here, you can get to this state, or you can get to this state, you can get to this state, all of these states depending on comparisons. And I ask, and I have already told you, adversary strategy is fixed. So, based on the adversary strategy, algorithm has a lot of choices of what algorithm comparison it can ask, it takes you there. Now, I am looking for a shortest path to go from here to here. Okay. Let us see how the shortest path is. I haven't filled up this table yet, but what I have is reasonably good enough. What are the two important things I want? I want this n to go to 0 and this 0 to go to n minus 2. Okay. If this n has to go to 0, what is the minimum number of comparisons I need? Let us look at the state here, right. This tuple changes by 2 at most, either it 2 or remains the same, or it might even get to 1, because in this case if it is an NL kind of thing, it will have this drops by 1, but this will something happen. So, it can drop by 1 or 2 or remains the same. So, but if I want to go from here to 0, how many comparisons are required? N by 2, because if I manage to do n by 2 many these kind of comparisons, I will get to 0. And note that in these comparisons, LW does not change. Okay. So, it is not that I am parallelly decreasing this and increasing this. No, in these comparisons, if I do this. So, basically what do I have to show? I have to show that in this huge graph of state of the algorithm graph, shortest path length is at least this much. That is what I have to show, and that is what I am trying to argue now, that the length of the shortest path from here to here, if this is S and this is T, it must be at least this. And why? So, here is my argument. Why? Because to go from n to 0, you need at least n by 2 comparisons, because this guy does not drop by anything larger than that. And to go from here to here, the way the adversary strategy is working out, LW will increase only by 1 every time. So, you need at least n minus 2 additional comparisons, because these guys which drop this does not increase this because of the strategy, right. Even if it drops by 1 like here, I make sure that this guy loses, this guy wins, so that LW does not increase. So, whenever this coordinate drops, this does not increase, and this to drop from here to here, you need at least n by 2 comparisons, and to go from here to here, you need at least n by 2 additional comparisons. So, together you need this many comparisons. Okay. Now, if you just look back at the algorithm, that is what it is doing, right. What is the algorithm doing? It is making this NN comparisons, right. That is the first round, never played, right. You are pairing them, you have done this n by 2 comparisons. So, that now you know that everybody has played something, and after that it continues to play win-win comparisons, WW, because so you made this guy drop to 0 already, everybody has played. Now, you are playing WW comparisons, so that this LW starts increasing, every WW comparison increases, right, because when you will find the max, you made some n minus 1 up to some n by 2 many this many comparisons, and then you will do n by 2 many LL comparisons on the first round losers. So, somehow an adversary strategy will tell you an algorithm like it did for binary search, and sometimes you can turn the algorithm and try and argue that somehow this is what the best algorithm should do, right. So, I have not written down much. So, what I want to say that the length of the shortest path from start to end in this graph, which I have not written down, is at least 3n by 2 minus 2. Okay, now we will see one more example, which is finding the median. Now, here is an example where sometimes the adversary may actually give away information. Okay, it just helps the proof. And even with giving away this free information, if I argue that you need to make a lot of comparisons, it still holds without giving away the information, right. So, we will see an example of how you will do that. Yeah. So, let us so again you are given a list of n elements. Let us assume all are distinct to make life simple. Let us even assume n is odd, and we want to find the median element, which is at least larger than n minus 1 by 2 and smaller than n minus 1 by 2 elements. Okay. So, what I will, the lower bound is, we will show very meager 1.5 n comparison. Anything more than n is hard anyway. That is all we are going to show. Okay, 1.5 n comparisons, and I said the adversary will actually give away a lot of information in between, and we will argue that it is still fine. Okay. So, the current best algorithm has some 3 minus epsilon n comparisons, and best lower bound is some 2 plus epsilon or something. So, it is not too far 1.5 n, but these things requires a lot more combination of decision tree and adversary kind of things. Okay, so what is the idea here, right? So, what let us see the state of the algorithm, right? What is it trying to find? Yeah, the state of the algorithm is, to start with, I have all elements in one bucket, and when I finish, I want some large and small. So, half the elements or n minus 1 by 2 elements should be here, and x this one element. So, basically I should be able to pair elements larger than this and smaller than x, and x sort of survives. Okay. So, the idea is this. So, what I am going to do, so this is 3 n by 2. I will say that for every 3 comparisons, I am going to throw away 2 elements out of contention of median. That is the idea. So, I will force you 3 comparisons, and after you made some 3 comparisons, I will say, these 2 elements, one of them goes to this big set U, other goes to L, and the other goes to S, and go find the median of the remaining. So, the problem, it is like this binary search, right. You made one comparison, I will answer in a way that, okay, now you search in this range, like that. Okay. So, the algorithm just makes some comparison, and I will answer it arbitrarily, and I am going to draw it vertically, means that this is larger and this is smaller. Okay. So, at any point of time, I have these kind of structures. Okay, and then maybe you will, let me just give you my adversary strategy, right. So, I am adversary and the algorithm both are going to maintain, this is the invariant. Okay. So, there is this L, there is S, and this is rest, and I will make sure that always L equal to S, and for any x in L, y in R, z in S, x is bigger than y is bigger than z. This is sort of the invariant the algorithm is going to maintain. Okay, that anything here is larger than anything here, which is larger than anything here. This is something an invariant algorithm will maintain. Okay. So, because since L is equal to S, the cardinalities, so the algorithm's job and the adversary job is basically to find the median of elements in R, because you do not need to even look at L and S. You find the median of R, it will turn out to be the median of the whole thing, because if you have partitioned it into something here, and I already told you that there are enough other elements which are out here and out here, their cardinalities are same. So, this is sort of the invariant algorithm adversary will maintain it, so that the job left is to find the median of elements in R, and when you start with everybody is in R, right, all elements in R, L is empty. Okay. So, this is something, and in R the algorithm is going to maintain the following structures, maybe some this, these are the only structures or the partial order structures maintained in R. So, what like I said, this means that this is larger than this means that this is larger than both these elements, this means that this is smaller than both these elements. Okay. Both of them will maintain only these structures. Now, you should ask, oh, how is it possible? Adversary will answer in a way that only these structures are going to be maintained, right. So, now let us say if you make a comparison between two elements of this type, but now I have to tell you the strategy like this, because a comparison can come from anywhere. If a comparison between two elements here, I will answer arbitrarily, you are wasting your time, why are you even comparing those elements? I told you, you really have to do this. So, but you do not know, because you are playing against any algorithm. So, some algorithm may ask a comparison here, just somehow answer consistently. Comparison here, answer consistently. Comparison here and here, based on this invariant, you say that this is larger than this. Comparison here, answer consistently. Now, I have to tell you comparisons here, how do I answer, right? Good. So, if two elements are in R and if both have never been compared, I will just answer arbitrarily and create this structure, right. Okay. Yeah, I haven't thought through completely, but I am going to make up. So, suppose you have this and some element is being compared with this, the answer is clear, I will say that this guy is larger and I will create this structure, right. Similarly, if this some element is compared with this, I will say this is smaller and I will have this structure. Okay. Now, suppose I have these two elements and let us say this is made, this comparison is made. Okay. What am I going to do? Any ideas? Let us see. See, remember, you have a choice to push some things to L and S. Of course, we will exercise that choice, because as I said, I am going to maintain only these structures. So, if this some comparison is coming between these two larger elements, push what in L? So, let me just name them so you can tell me. What is larger, smaller? You have a choice, you haven't answered it. So, you can answer in whatever way you want between B and D. So, yes, what can you do? B to L, C to S, right. So, now what I do is I will say look, I will say B is larger than D and I will push B to L and C to S, and now what is left is only these two about which I do not know. So, I am back to this structure, right. I am back to this structure, I maintain these invariants because every time I push something here I also push something here, and it is consistent with whatever. All I am now, what am I saying? This is extra information I am saying, hey, this A, so or this B which you said is larger than D, not larger than just D, anything else in R, B is larger. This is the extra information I am giving it. Similarly, this C is smaller than anything else in R. I will throw that in S. Extra information I have given. Now you are back to this structure of A and D sitting there. How many comparisons have you made? This picture should tell you how many comparisons you made. 3 comparisons we made. We threw 2 elements out, right. Basically, now the algorithm's job is to find the median. So, by throwing all this, what does it mean? I am actually constructing a worst case input. The adversary is constructing a worst case input, and in that worst case input, this B will be larger than anything in R now, C will be smaller than anything in R. Assuming that this is the structure, that means that you have not played anything else, so you are comparing this. And you have made 3 comparisons. I forced you to make 3 comparisons to gather this information of throwing away 2 elements. Now, let us see the other possible comparisons, but this is the idea, right. So, what I want to emphasize is that adversary can give away some extra information, just helps the proof. What other comparisons you may want to make? I do not know, like I said, I have not completely, okay. Let us say you made this, now I am making a comparison like this, because I am making this structure, so a comparison can be made with anything. If you make this comparison, what can I do? I will just say, hey, this guy, push him to L and push any one of them, maybe push this one to S. I made 3 comparisons, these 2 elements are gone and I have left with these 2 elements there, right. So, all I have to argue is that for every pair of comparisons, I have a way of answering so that these invariants are maintained. Okay. So, let us try one more and then I will let you complete it. I do not know, what if you make a comparison like this? Yeah, these are some good cases, right. What can I do? Let us call this A and B. I will push A to L and B to S, and how many comparisons I have spent? 1, 2, 3, 4, 5 comparisons I have managed to do. Now I am left with all these things about between which there are no comparisons anyway. So I am back to this structure. I will throw this into these structures. Okay. So now you just have to argue that for the adversary is just maintaining only the structure in R, and for any possible pair of comparisons algorithm makes. So I mean, you do not know, it might make something like this, that adversary has a way of answering in a way that at least 2 elements are eliminated, at least 3 comparisons are forced. Okay, if this happens, do the same thing, make A the push him up and push this guy down, right. I can't push this because these are larger than this element, so I will push this guy down. I made a lot of comparisons, 5 comparisons and 2 elements are out. Yeah. So I just have to argue that for every pair of comparisons. So, I maintain only these structures for every pair of comparisons. Adversary has a strategy to answer in a way that it is forcing at least 3 comparisons and 2 elements are eliminated. And the 3 comparisons about which, the remaining elements, they are back to this square here. Nothing has been, nothing about them. So now, from here to get to here, it was like 4 or 5 papers to get from 1.5 n to 1.75 n, it moved on, it's staying at 2 plus epsilon. So again, the thing I want to mention is that sometimes the adversary may actually give away the information, it's useful. So now I'm just going to end with some exercises for you to try. I already gave you 2 exercises, right? One, merging is what I gave in the comparison model. Let me just give you some adversary lower bound exercises. So one is you want to merge 2 lists each of size n. Show 2n minus 1 comparisons lower bound. Right, 2 sorted lists, each of size n, and you want to merge them together. Each one is individually sorted, you want to merge them together, and now you want to, and there's a very simple algorithm which you just compare the first pair, and that takes something like 2n minus 1 comparisons. Show that that's actually optimal using an adversary argument. So you have to answer. So what should the adversary say? That, oh, if I pick an element from here, an element from here, and algorithm compares, how would you answer? You should have a strategy for it so that you can show 2n minus 1. Right? An algorithm may actually pick an element from here, 2 elements from here, and ask the question. It's a stupid algorithm, but it's sorted, so you consistently answer. You should be prepared for all kind of questions. So you should have a strategy. So how would you answer a comparison so that you can show 2n minus 1 lower bound? Okay, and the B is, does the same kind of a lower bound hold to merge a list of size m and one of size n. I mean, is it important that both lists are of same size for the 2n minus 1 lower bound? Even if they are different, will you have the same lower bound? Will the same adversary work? Okay, so here is I can give you more, but they are not just simple adversary, it requires more, so which we might take up tomorrow. So here, so you know what a tournament is, right? A directed graph. You can think of it as an orientation of a complete graph. And take a complete graph on n vertices and arbitrarily orient every edge. What you get is a directed graph, it's called a tournament. In other words, it's a directed graph where between every pair of vertices there is exactly one directed edge. Okay, there is an edge between every pair directed in some way. Okay, and you want to find a Hamiltonian cycle in a tournament, okay, or does it exist is a question. You can actually solve it in polynomial time, but I am going to ask you to show a lower bound for it. Okay, so let's see. So So, show that Tn, let us call it a tournament on n vertices, has a Hamiltonian cycle if and only if it is strongly connected. You know what a strongly connected directed graph is, right? What is a strongly connected directed graph? Yeah. So, between any two vertices is a path from A to B as well as from B to A, if such a graph is strongly connected. So, what I am saying is tournament has all edges, right? Every pair has a directed edge. So, what the claim is that, so clearly if any graph, any directed graph is, if it has a Hamiltonian cycle, then it is strongly connected, right? Because between any pair of vertices you can, there is a path, right? Right. If I have a Hamiltonian cycle, let us say it goes in this, you want to go from A to B, here is a path, and if you want to go from B to A, there is a path. Right. If you have a Hamiltonian cycle, there is a directed path between any pair of vertices. What this is saying is, in a tournament, yeah, so if it has a Hamiltonian cycle, it is strongly connected. This is true for any graph, any directed graph. But for tournaments, the converse is also true. Oh, by the way, every tournament has a Hamiltonian path. That is another interesting exercise. Maybe I will write that out as well. If you care about a Hamiltonian path, it always exists. Okay. But so far, nothing about adversary, but fun exercises. And can be found in it's even better. I don't even have to look at all edges. You can actually find it in n log n time. Okay, there are n square edges there. I don't even need to find all, look at all edges. You can actually find the Hamiltonian path, directed Hamiltonian path in any tournament in n log n time. It's nice, divide and conquer. It has some connections to sorting. You can do it. It's a good, nice exercises. Okay, so prove. Now, what I want to say is, give an omega n square lower bound to find a Hamiltonian cycle which is the same as so here use an adversary argument. Okay. Basically, you have to say that any algorithm must find more or less every edge. Look at every edge. You can't just determine whether it has Hamiltonian, determine whether it is strongly connected without looking at not every edge, but a fraction of the edges at least. So, this is a fun, I mean, in fact, yeah, all these are easy. You can, I mean, another star exercise is to come up with an algorithm n square algorithm is not that easy, but n square lower bound is not hard. So, here you can think of an adversary, can give away some information, and adversary can force the algorithm to look at certain set of edges, a fraction of the edges. Okay, any questions on the questions? Clear? Yeah, okay. We'll continue tomorrow then.